Welcome to today's lesson. I'm Shemasaka Kendins, and so today we'll look at a lesson in physics. In particular, we'll look at the principle of moments, and so we'll develop concepts where we can apply these principles so that we can solve even more complicated problems. And so we go straight into the lesson. Well, earlier on in the other lesson, we looked at the moment of a force. And so if we have several moments of a force about a point, we can be able to develop a principle. And this is what we are looking at today. We are looking at the law of moments, or the principle of moments, which states that if a board is in equilibrium, the sum of the clockwise moments about any point is equal to the sum of the anti-clockwise moments about the same point. What it means is that there should be a turning point, which is the pivot. And so the moments which will be actually putting the body in the clockwise way should be equal to the moments putting that same object in the anti-clockwise way. We'll see it very clearly as we go now in depth. Okay, so in simple terms, we are saying the sum of the moments in the clockwise manner should be equal to the sum of the anti-clockwise moments. And so, in other words, you sum up all the moments in the clockwise and then sum up all the moments in the anti-clockwise and equate them. And these, according to this principle, they will be equal. And so here is a very basic example which can help us to really fully understand this concept. Imagine you have a uniform load which is pivoted at the center. What it means is that if you have a load and it's uniform and it's pivoted at the center, it means that it can balance. So the center of mass for the load is in the middle, and therefore there are no moments for this rod. And so now you put forces 1, 2, and 3, which are resting on the load at distances D1, D2, D3 from the pivot respectively. If the system is in equilibrium, then apply the principle of moments. If this system is balancing, after you put these 3 forces, then we say the system is in equilibrium. And so this is what it means here. We have our fulcrum here, which is the pivot. And then we had to put this rod here, which is uniform. And they said this rod actually is pivoted at the center, meaning that since it's uniform, it balances. Before you even put any forces or any masses on it, it balances. So it means that it has no moment at all when it's balancing. Okay, and so now you place the forces here, or you exert some force. Force 1 there, you put it, and you put an object here which will exert a force, which is force 2, and you put another object here which will exert a force downwards, which is force 3. And force 1 from the pivot is a distance D1, and force 2 from the pivot is a distance D2, and force 3 is a distance from the pivot, which is D3. And so according to principle of moments, we are saying the moments in the clockwise should be equal to the moments in the anti-clockwise. So you sum them. So we can identify here which moments are in the clockwise. Definitely F1 is pulling this way, the way the clock moves. So it is in the clockwise. So there is only one which is pulling in the manner, the way the clock hand moves. So this is a moment. So the moment here in the clockwise, it will be F1 multiplied by the distance to the pivot, which is D1. Those which are pulling, like this force here, it is pulling this way in the anti-clockwise. So the moment for force 2, it will be F2 multiplied by the distance where it is to the pivot. So it will be F2 multiplied by D2. That is one moment. And then the moment for force 3, it will be F3 multiplied by the distance to the pivot, which is D3, the distance D3. And so here we have seen that in the anti-clockwise, we have two moments. In the clockwise, we have one moment. And therefore, verifying the principle of moments would say F1 multiplied by D1 should be equal to F2 multiplied by D2 plus F3 multiplied by D3. And exactly this is what we have done here. So in the anti-clockwise moments, there are two moments which we have added. That's why they say sum of the anti-clockwise moments. While in the clockwise, we have only one moment, which is F1 multiplied by D1. And so I thought this is very important because even before we put figures, we need exactly to understand what is meant by the principle of moments. Really, we cannot proceed to understand more complicated problems if we do not understand this basic principle. In other words, I will repeat briefly to indicate that in the clockwise manner, we have one force which is pulling in the clockwise, and therefore its moment is F1 multiplied, which is the force, multiplied by the distance to the pivot, which is D1. In the anti-clockwise manner, we have two moments. The first one is force number 2 multiplied by the distance to the pivot, which is D2. Another, in the anti-clockwise, the moment we have about the pivot, it is F3, which is force 3 multiplied by the distance to the pivot, which is distance 3. And so this is basic and very important. If we don't understand it, it means that we cannot proceed to understand more complicated problems. And so now, again, we give another example. Well, now this load is not lodged at the center. This is on the second part. The rod is not pivoted at the center, meaning that its center of mass would be not at the pivot, and therefore it will also be considered, okay, in the moments, because now its weight will be actually a force which is pulling down. And so this is an addition to the second concept. So when the weight of the load is not at the pivot, it means that that object or that rod in our case, it has a moment. Then the moment will be at the center of mass, which is the weight of that object. So this is the rod, which is not pivoted at the center. It is uniform, but it's not pivoted at the center. So its center is here. For example, if this rod here was 100 centimeters, So at the center here, 50 centimeters, that is where the center of mass is, or where the weight of the object is concentrated, and therefore it has created a force which is known as the weight. And so now we have to include that in the clockwise manner, we are going to have another force which has been created by this rod, which is not pivoted at the center. Its center is at this point here, which is W. And therefore, now let's apply the principle of moments to this system where the rod is not pivoted at the center, and therefore the weight or the center of mass lies outside the pivot here. Therefore, the rod, before you even put the mass around, this rod will fall this other in the clockwise manner, to fall this side, because it is more heavier this side because of the center of mass, which is actually not at the pivot. This is a very important concept. If something is uniform and is not pivoted at the center, it creates a moment from the pivot. Therefore, the rod alone, it has a moment about its center of mass, which is actually the distance m multiplied by where the center of mass is, or the weight of that object is, which is W. And so now let's apply the principle of moments on this system. So in the clockwise manner, we have two actual moments, which is F1, which is force number 1 for this object, multiplied by the distance D1 up to where the pivot is. Again, we have another moment, which is created by the rod, where its center of mass is, or its weight is, which is W multiplied by the distance where to the pivot. And then you add these two. This is what we have done here. Okay. Now, in the anti-clockwise moments, we have actually force number 2 created by this object multiplied by the distance up to the pivot, which is D2, which is this one we have done. And then you add the force created by the actually object, this object here, which is force 3 multiplied by the distance to the pivot, which is D3, and you add them. So you add the two moments in the anti-clockwise direction. And if the system is in equilibrium, or what it means, you need to be in equilibrium. If it balances, it means that the moments which we have added in the clockwise should be equal to the moments which we have added in the anti-clockwise. This is very important. So the addition of a concept here, which we have added, is that if you have an object, before you even balance it, and it's not pivoted, and it's uniform and it's not pivoted at the center, it creates a moment. And that moment will be at the center of mass for that object, or at its center. So imagine we have not put this object, and this object, and we balance this rod. And this rod, we don't put it at the center. Don't put the pivot at the center. It means that it will fall this side. Okay, to fall in the clockwise manner, meaning that its center of mass will still be at the center here. Okay, and so we proceed. Now, this is what I was explaining already, that you add the moments in the clockwise manner and the moments in the anti-clockwise manner, which you have already done. And so I feel now we can look at the equation basically to apply the principles which we have learned. And the two principles are very basic and very important. If we have not understood them, I actually urge you to go back and understand them before you really tackle the questions. And so now I'll proceed to the question. Here is a uniform meter rule. Uniform meaning that the mass in that ruler is evenly distributed, and therefore it is pivoted at 20 centimeter mark from 0. So we have a meter rule which has marks from 0 to 100, and they put the pivot at 20 centimeters starting from 0. So at 20 centimeters, that's where the pivot is. And then a mass of 20 grams is placed at the 4 centimeter for the 0 mark. And then we place another mass here at 4, starting from 0 here, 4 centimeter, they put a mass there. And they say, calculate the mass of the meter rule if the system balances in the on the pivot. What it means that if it's in equilibrium, when you put this object, it is two balances. Okay, so what is the other force which is enabling to balance? And that force will be the weight of the meter rule. And where is the weight of the meter rule? Is at its center. That is at 50 centimeters. And therefore, it means now we have to apply the principle of moments to find the actually the mass of the meter rule if it balances. So from the 50 centimeter mark to this 20 centimeter mark, from 20 centimeter mark to 50 centimeter, the difference here, they are 30 centimeters. And from the 20 centimeter mark to the 4 centimeter mark, or from the 4 centimeter mark to 20 centimeters, here they are 16 centimeters. And therefore, if the moments, if this system balances, it will mean that we have to multiply the mass of the roller, which is m, multiplied by this distance, which is 30 centimeters. This is the moment in the clockwise manner. And in the anti-clockwise manner, this object here will be pulling down here at a distance 16 centimeters to the pivot, and therefore it will be the mass of this object, which we say it is 20 grams multiplied by 16 centimeters. And this is what we have done. M is the mass of the ruler at, okay, mass of the ruler, and the distance from where it is to the pivot, since it is 20 centimeter, it is actually 30 centimeter. This is the clockwise moment, which should be equal to the mass which is placed on the ruler at the 4 centimeter mark, which is 20 grams multiplied by the distance to the pivot, which is 16 centimeters. Okay, and therefore we can multiply the two and then divide by 30 to find the mass of the ruler. So the mass of the ruler will be this multiplied with 20 grams multiplied by 16 centimeter divided by 30 centimeter. And centimeter here and centimeter will cancel. And then we can divide 20 multiplied by 16 divided by 30, which gives us 10.7 grams. So this is the basic principle. And so here, the principle which we have applied, or the concept we have applied, is where an object is not pivoted at the center. And therefore, the center of mass is at the center of that object or that rod. And therefore, it creates a force at its center. And so we proceed now to another application you note that it's not always that on the same side, the forces will all be actually in the clockwise direction, as we shall see in this part of the question. And so it's important to be able to know how to identify which forces are in the clockwise and which forces are pulling in the anti-clockwise. And so here we have a 70 Newton beam. So we have a beam here, which is 70. This is 70 Newtons. Okay, and it's not pivoted at the center, meaning that its weight at the center, if this is 70 Newtons, okay, if this is 70 Newtons, so at the center here, it has a weight 70 Newtons. Okay, it is suspended by a rope from the roof. So on the other side at the end, they have tied a rope, and there is such the roof there. This is tied to the roof to the rod, meaning that there is a force pulling it upwards for it not to drop this way, to drop in the clockwise. So there is a force here which is pulling upwards. And you see, if you see, this force is pulling in the anti-clockwise direction. It's pulling this way in the anti-clockwise direction because it's pulling towards the roof. The beam is resting on a pole as shown. So this beam actually is resting here. Okay, it is resting here. So this becomes our pivot to support this system, either to fall in the clockwise or to fall in the anti-clockwise. And therefore, this is our pivot where there is a pole here. Okay. Forces F1, which is 5 Newtons, and force 2, which is 20 Newtons, are resting on the beam. And so they have put a force 1 here, which is 5 Newtons. And this one is pulling in the clockwise direction because it's making this thing to fall downwards here. And the weight, as we said, which is at the center, is also pulling in the clockwise. It's the 70 Newtons. And it is 1 meter from the pivot. And this weight, it is 2 meters from the pivot. And so, calculate the tension on the supporting rope tied to the roof if the system is in equilibrium. So I say, if this rod is to balance, meaning that it is in equilibrium, what would be the force which would be on this rope? Okay, a force on a rope, it is known as a tension. And therefore, we have identified here, actually, we have identified the clockwise moments. The clockwise moments is force number 1, it is pulling this way. So its moment is force 1 multiplied by the distance to the pivot, which is 2 meters. The second moment is the weight of this rod, which is a W multiplied by the distance to the pivot, which is 1 meter. So in the clockwise, we have 2 moments. F1 multiplied by 2 meters, or 5 Newtons multiplied by 2 meters, plus 70 Newtons multiplied by 1 meter. Okay, in the anti-clockwise, we have force 2. This one is pulling this way, which is 20 Newtons multiplied by the distance to the pivot, which is 3 meters. Plus this one here, it is pulling upwards. If you see, it's pulling in the same direction, this one, anti-clockwise. And so this is a very basic concept it doesn't mean that if we have the pivot here, all the forces which are on the right this side are actually pulling in the clockwise direction. No, it doesn't mean that. You have to identify in which direction that force is pulling. You have seen that this is on this side, this force on the tension here is on this side here, but it is pulling in the anti-clockwise direction. So this is a basic concept which we should all understand, that actually it's not always that if you have forces in one side, it means that they are pulling in the same direction. You have to identify. And in this question, we have identified that actually, even if this force T is this side, on the same side as F1 and W, but this force T is pulling in the anti-clockwise direction because it's pulling upward so that this pole does not drop in the clockwise direction. And so I thought this is a very basic question which can help us to understand principle of moments. And so let's apply now the principle of moments. So we are saying in the clockwise direction, we have the 70 newtons, which is created from the rod, which is not pivoted at the center. So it is 70 multiplied by 1 meter plus 5 newtons multiplied by 2 centimeter, which is the distance to the pivot. Those are in the clockwise direction, which should be equal to 20 multiplied by 3 meters, the distance up to the pivot to the pole, plus T, which is the tension, which is identified that is in the clockwise direction, multiplied by the distance to the pivot, which is 5 meters. And this is what we have done here. And therefore, now we can multiply 70 times 1, it is 70 Newton meter, 5 Newton multiplied by 2 meters, which is 10 Newton meters, and 20 Newton multiplied by 3 meters, which is 60 Newton meters, plus tension multiplied by 5 meters. And now we can actually subtract. We bring this one this side, meaning that we are going to subtract 80 newtons minus 60 newtons, which is equal to tension multiplied by 5 meters. And the tension, we can find it by actually saying 80 minus 60, which is 20 Newton meter divided by 5 meters. And this meter and this meter will cancel. And we say 20 newtons divided by 5, which gives us 4 newtons. Therefore, the tension is 5 newtons. So this is the end of the lesson. And so I thought we have actually delivered the message on how we can apply the concepts in principle of moments. And so you can actually subscribe to my YouTube so that you can get more of these lessons. And these are very interesting and very basic concepts which can help us to solve even more complicated problems. I thank you.